Okay, good evening, everybody. Before we start the session today, just one announcement. The chapter 19, our assignment will be posted tomorrow, and the deadline for completion is Sunday, March 2nd. Sunday, March 2nd. Okay, that is for chapter 19, our assignment. Okay, for today's session, we are going to start our discussion on chapter 19. Chapter 19 is concerned with the chemistry of aldehydes and ketones. Fortunately for this chapter, many of the reactions we have done in previous chapters, so hopefully a lot of what we are going to be discussing will be sort of like a review for most of you. Okay, for this chapter, you do have a lot of reactions and a lot of reaction mechanism, and so therefore, upon completion of this chapter, I will expect that you will be able to use this list of items and concepts on this slide as a study guide. For example, if you take a look at item number 10, you should be able to write a mechanism for conjugate addition reactions. So you need to know what conjugate addition reactions are, and of course the mechanism for those type of reactions. And also, if you take a look at item 11, there will be a lot of synthetic designs, synthetic schemes. So not only do you need to know what those reagents do, you need to be able to put them together to make organic molecules. Okay, so now let us ask ourselves, of course, all of you guys know what aldehydes and ketones are by now. Just for formality, aldehydes and ketones are those organic compounds that contain the carbon-oxygen double bond, which we refer to as carbonyl group. In the case of aldehyde, the carbonyl group is attached to hydrogen. This is an aldehyde right here. Hydrogen attached to carbonyl, and in most of the cases, the carbonyl is also attached to a carbon atom, which is right here. So this is an example of an aldehyde. Of course, as you can see in this molecule here, whether we call a molecule an aldehyde or any other class of compounds depends on our focus. In this particular instance, our focus is on the aldehyde functionality. So we say this is an aldehyde. In the case of a ketone, you can see here you have a carbonyl. The carbonyl carbon of a ketone is attached to two carbon atoms. Here, you have a carbon here and another carbon here. And that is what will make a ketone. In other words, a carbonyl that is attached to two carbon atoms. You also see here, this part of the molecule also gives us an example of a ketone. You have the carbonyl here, carbon here, and carbon here. Okay. Now I show you these two molecules here to also let you know the importance of aldehydes and ketones in our everyday life, particularly with regard to the metabolic activities in our body. These two molecules here are pyridoxal phosphate and hydrocortisone. These are metabolic hormones that are used in various metabolic processes in our body. Very important molecules indeed. Indeed, most organic reactions that take part in our body, for the most part, a lot of these actually do involve a lot of ketones. Okay? Okay, so now let us begin our discussion in terms of the nomenclature of aldehydes and ketones. The simplest aldehyde, we are starting here with aldehyde. The simplest aldehyde is this molecule here, which we commonly refer to as formaldehyde. As you can see, unlike the other aldehydes, in formaldehyde you have two hydrogen atoms attached to the carbonyl carbon. Okay? We also have the next in the line of molecules that constitute aldehydes will be the ethanol, this here, in which you only have two carbon atoms. As you can see here, the IUPAC name is derived from the name of the corresponding alkane name. For example, we call formaldehyde, the IUPAC name is methanol. So where does that come from? Comes from the name methane. And so what do we do to derive the name of the aldehyde? We remove the E ending and we replace with the suffix al. Okay, so this is the suffix for aldehyde. Okay, so therefore we call this methanol. In the case of this molecule here with two carbon atoms, we refer to this as ethanol. Now, in the case when you have the aldehyde functionality is attached to a ring, then what you need to do is to give the name of the full name of the ring, and then you use the suffix cap aldehyde. Cap aldehyde. Okay. For example, this molecule here, we refer to this as cyclohexane cap aldehyde. Yes. Well, that is the name we give it. In other words, if you have this the aldehyde functionality this here, if it is attached to a ring, okay, to give the IUPAC name, what you do, you give the name of the full name of the ring, and then you add the word cap aldehyde. Okay, for example, if we have this, if we have this molecule here, what are we going to call that? What are we going to call that? Cyclobutane cap aldehyde. Yes. Okay. So this becomes cyclobutane cap aldehyde. Okay. Now, supposing we have more complex aldehydes. More examples. More examples of aldehyde nomenclature. In this case, IUPAC nomenclature. Okay. If we have this, okay, what are we going to call this? What To give the name of this molecule here, you have to look for the longest carbon chain that contains the aldehyde functionality, which is this here. You look for the longest carbon chain that contains the aldehyde functionality. In this case, what would that be? Of course, this carbonyl carbon will be carbon number 1. So what would be the longest carbon chain? You see hexane? Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Is that right? Okay, very good. Oh, sorry. Okay, so you look for the longest carbon chain that contains the aldehyde functionality. So therefore, oh, something is wrong here. So, therefore, we have in this molecule here, we have two substituents on carbon number 3. So what would be the name of this? What would be the name of this? 3, very good. 3 diethyl, right? Okay. XR. Now, okay, because in this case, this is a substituent, the ethyl group right here, and this is another substituent. Now, supposing we have this molecule here. Okay, how do we name this? In this case, you have this molecule contains the aldehyde functionality. It also has an hydroxy group. In this case, the aldehyde will take preference. Okay, the preference goes to the aldehyde. So we have to name this as an aldehyde, and therefore we start numbering from carbonyl carbon of the aldehyde, which will always be carbon number 1, 2, 3, 4, 5, 6, and 7. And in that case, the hydroxy group will be a substituent. So therefore, we are going to call this 5-hydroxy hepta now. Now, supposing we have an aldehyde functionality and a ketone functionality. Supposing we have this. In this case, once again, the aldehyde will have to take preference. And now we are going to name the carbonyl of the ketone as a substituent. To name the carbonyl of a ketone as a substituent, you use the word oxo. So this becomes an oxo group. In this case, the carbonyl of that ketone becomes an oxo group. So therefore, what will be the name of this molecule? Carbon 1, 2, 3, 4, 5, and 6. So this therefore becomes 5-oxo XR now. Okay? Well, if you have a carbonyl of a ketone, and then you also have an aldehyde in the same molecule, Okay, you have to give the name. You have to name that molecule as an aldehyde. Okay, and therefore the carbonyl of the aldehyde becomes a substituent of the aldehyde, and the substituent name for that carbonyl is oxo. Okay. Just like we have methyl, ethyl, okay, hydroxyl. Okay. Now, supposing we simply just have the ketone. Now, let us go to nomenclature for ketone. Of course, the smallest ketone is this molecule here, and the common name for this is acetone. That is the common name for that molecule. But the IUPAC name for this is 2-propanol. As you can see here, the name is also derived from the name of the corresponding alkane. If you recall, corresponding alkane will be this here, and that name will be propane. So what do? We remove the E ending of the corresponding alkane, and we then add the suffix O-N-E. Okay, so the suffix O-N-E is an indication that you have a ketone in that molecule. Other examples, if we have this here, the corresponding alkane name for this will be what? What will be the corresponding alkane name for cyclohexane? Very good. And therefore, we remove the E ending of cyclohexane, and we add the suffix O-N-E, so this becomes cyclohexanone. Okay. Okay, other examples. More examples of nomenclature. Okay, let us say this is my left and this is my right. Okay. Now, to name this molecule, you have to give the lowest possible number to the carbonyl carbon of the ketone, the lowest possible number. So, given that information, where do we start numbering this molecule? From the left. Very good. 1, 2, 3. 5, 6, and 7. So therefore, this becomes 3 heptanone. Okay. Now, if you have substituent, you have to indicate the names of the substituent appropriately. For example, if we have this, okay, once again, this is my left and this is my right. Where do you think we need to start numbering? From the left. Keep in mind you have to assign the lowest possible number to the carbonyl of the ketone. So therefore, this becomes 1, 2, 3, 4, 5, 6, and 7. Okay, so that means we have substituent in the 6th position and another substituent in the 5th position. Of course, we still have to follow the rules of alphabetizing. So therefore, what would be the name for this? 5-bromo, very good. 5-bromo. Okay. 6-methyl. And then indicate the position of the carbonyl of the ketone. 3 heptanone. Okay. So I'm going to leave the rest of nomenclature to you guys. Checking your book. Your book has a fairly good treatment of a nomenclature of aldehydes and ketones. Yes. Yes, you could. Yeah, you could do that. Yeah, you could do that. In other words, what you want us to do, we could also name this as we also say this would be 5-bromo 6-methyl hepta 3 on. Yes, you could do that. And that will also be the name for this molecule here. Okay, yes.
So for aldehydes, you don't have to indicate the position of the carbonyl?
Yes, for aldehyde, the position number 1 is assumed as belonging to the aldehyde carbonyl. Yes. You do not have to indicate the position of that carbon. Yes. Okay. Oh, very good. Now, so now at this point, let us now begin the synthesis of aldehydes and ketones. Most of, like I told you before, most of this we've done before, so it should not be new to most of you guys here. So let us start. Synthesis of aldehydes and ketones. Let us start with oxidation of primary alcohol. Oxidation of primary alcohol. If we take a primary alcohol, use this here. And I want to make this aldehyde what reagent do I need to do that? What reagent? PCC, very good. Okay, PCC, which is pyridinium chlorochromate. Like I said, all of this will be reviewed to all of you here. Or what other reagent can we use? Desmartin. Or Desmartin pyridinine, but you don't have to. You just say Desmartin, that is fine. Okay, these are the two reagents that we could use in order for us to make an aldehyde from a primary alcohol. Now we could also do oxidation of secondary alcohol to get a ketone. Okay, let me say this here to get aldehyde. oxidation of secondary alcohol to obtain a ketone. If I have this cyclohexanol, okay, what reagent do I need if I want to obtain cyclohexanol? We will use chromium trioxide, right? We could use chromium trioxide. We could also use PCC and desmatting. So let's go to the next page. Starting with the same. We could also use PCC or desmatting. I mean the solvent? No, you don't necessarily. In other words, the dichloromethane this here, this is just the solvent. You don't have to. Just if you have it, that's fine. But if you don't, that's fine also. Okay. Okay. We could also obtain aldehyde from esters. Reduction of esters to obtain aldehyde. If I have an ester, let's use this. And I use this molecule here. Right now I will just give you the acronym. I will write the structure here in a few seconds. What we call dibah. D-I-B-A-H. Step 1. And then step 2, hydronium ion. This molecule here, dibah, will transform an ester to an aldehyde. So that is a very important reagent. No, there are not too many reagents that will do that. And what is dibah? Is this molecule here. We call this diisobutyl aluminum hydride. And we use the acronym dibah. So for you, in all subsequent reactions, just simply indicate dibah. You don't need to write this big molecule here. Okay, the D is from the di, the I from the iso, B from the butyl, A from the aluminum. Of course, the hydride is hydrogen. Okay, very specific for transforming an ester into an aldehyde. Now, you guys should be able to write the mechanism for this reaction. Why do I say that? Because what dibah does is to produce an hydride. In other words, this hydride here, all it does is to supply an hydride. Okay, so given that information, can you therefore give me the mechanism? If I go from here, can you give me the mechanism going from here using diabol to here, going from that ester to this aldehyde. Okay, anybody want to try? Keeping in mind that all this does is to supply the hydride. Okay, so you start with the hydride. So what is going to guess? Oh, very good. Attack the carbonyl carbon. Very good. So the hydride will be acting as a nucleophile, and the carbonyl carbon is an electrophile, right? And this pi electron goes to here. So therefore we have this. It's a different color pen. Okay, so we form this alkoxide intermediate with the negative charge on oxygen. So what is next? Yes. Here. Okay, excellent, excellent, very good. So we are going to regenerate the carbonyl carbon, and in so doing, the methoxy will be kicked out of this molecule, because carbon can only have 4 bonds. Okay, so therefore we have this. Okay, so why do we need the acid at the end? This dilute acid at the end, yes. Huh? Yeah, oh, you are going to, yes. Okay, so now the acid at the end, what does it do? Simply just protonate this here, okay? Just protonate the methoxy that we kicked out of the ester. So the methoxy pick this up and this here. So at the end you have your aldehyde product plus this here. And also, sometimes the dilute acid will help us to destroy any leftover diabol. Yes. Which one is?
Because H308, like you didn't give us that in the beginning as a product. So if you don't give us that as a product.
Oh no, this here. No, we're not worried about this. Although you don't have to, don't worry about that, because you've already, all we're doing here is just kicking this out anyway. So that's fine. Okay, so so we could make an ester from an, we could make an aldehyde starting from an ester by reacting with a diol. Okay, was that number 4 reaction? Synthesis, okay. Continue. Continue. Oh, that was 3. Okay, so now this is 4. So we are still continuing on the synthesis of aldehydes and ketones. So this will be 4. Oxidative cleavage of carbon-carbon double bond. We've seen that before. Of carbon-carbon double bond using ozonolysis. Okay? So if we take this, the product you obtain here depends on the nature of the carbon-carbon double bond. If we take this molecule here, in which we have a carbon-carbon double bond, let me go ahead and number this. This is carbon 1. Let's say that, well, let's call this 1, 2, 3, 4, 5, and 6. Carbon number 1 is attached to no hydrogen atoms. Okay. On the other hand, carbon number 2 is attached to 1 hydrogen atom. So therefore, if we do this ozonolysis, and then we follow that up with zinc in dilute acid. This is the reagent we use for ozonolysis. Okay, which of the carbon will become the carbonyl of an aldehyde? Which? 2, exactly. Okay, the carbon that is attached to hydrogen becomes the carbonyl of an aldehyde. Okay, and the carbon that has no hydrogen attached to it becomes the carbonyl of a ketone. That we already know. So therefore, the product will be this. Keep in mind what the ozonolysis does. What this reagent does is to cleave the carbon-carbon double bond, so that each of those carbon becomes a carbonyl carbon. Keep that in mind. So on this part of the molecule here, this is our ketone here, and this is our aldehyde. Of course, if this molecule that we are starting with, if this metal here was an hydrogen, then we are going to get a dialdehyde, right? Okay, so that is our oxidative cleavage of carbon-carbon double bond. So you could imagine all kinds of possibilities that you could do. Another possibility would be, for example, if we have this. Okay, supposing I do that. Step 1, ozone, and step 2, zinc in dilute acid. What will be the product of this here? What will be the product? We get a ketone and an aldehyde. In this case, the simplest aldehyde. Because we are going to cleave this. We are going to cleave this. This here becomes formaldehyde, and this here becomes, in this case, the ketone, cyclohexanone. Plus So we get formaldehyde, and then we also get cyclohexanone. Okay? This carbon here is this carbon, and of course, this here is this carbon. Okay. Now about number 6. Synthesis number 6. Number 5? Okay. Okay, number 5. Okay, mercuration, demercuration. Mercuration, demercuration of carbon-carbon triple bond to give ketones. This also, we've seen this before. So if we have this, and we use this reagent here, mercury sulfate. Okay, so I hope you guys are putting together your list of reagents. Mercury sulfate in the presence of sulfuric acid. This reagent here, what it does is to transform one of the carbon-carbon triple bond to a carbonyl and the other carbon to a CH2. Okay? This carbon here is this carbon, and this carbon here now transforms to a CH2. Okay? That is what this reagent will do with a carbon-carbon triple bond. Yes, Adeline? Yes, in this case you get it, since we are starting with a symmetrical molecule, I did that on purpose. Yes. You could have the carbonyl on this carbon here and this CH2 on this here, yes. But if you do not have a symmetrical molecule, you are going to get a mixture of ketones. Okay? You follow that? Okay. Okay. Now, if you have a terminal alkyne, still on number, still on number 5. If you have a terminal alkyne, in other words, a carbon-carbon triple bond at the end of the carbon chain and you use the same reagent, mercury sulfate in the presence of sulfuric acid. Okay, in this case, you are going to get a methyl ketone. You are going to get a methyl ketone. Now, the reason for this is because this reagent here, what it actually does, do you have a question? What this reagent actually does is to add water across the carbon-carbon triple bond in a mechanical fashion. Okay, it's a mechanical addition of water. And mechanical addition of water, across the carbon-carbon triple bond. Okay, in that case, the hydrogen goes to this carbon here, and the OH goes to here. The hydrogen goes to this carbon here, right here. So now we have two hydrogens here, and the hydroxy goes to this carbon here. And as we told you in the previous chapter, this is called an enol. This is an enol. And enols are very unstable molecules that will rearrange very easily to the corresponding ketone or aldehyde. Okay? Just a minute, let me Okay, this is an enol that will rearrange very easily. It's in equilibrium with the keto form. So what happens? The proton will break away, form a carbon-oxygen double bond, and this pi electron comes here. And the net process is you are going to form the methyl ketone. That is how you get the methyl ketone right here. Okay. Now, these two molecules here, the enol and this ketone here, we refer to each one of them as being tautomers of each other. Ordinarily, we would say they look like constitutional isomers. But because they will convert to each other at room temperature by simply moving the hydrogen around, you see what we've done here, we simply move the hydrogen from oxygen to this carbon. Okay? So therefore, we refer to this, let us call this molecule A and molecule B. A and B we refer to as tautomers of each other. And this is the keto form, and this is the enol form. Okay? Well, the point to be made here, therefore, is anytime you have a terminal alkyne, and you use this reagent here, you get a methyl ketone. Now, okay, that will be, what number is this? Jodina, what number? Now going to 6, okay? Now, hydroboration oxidation, hydroboration/oxidation will also react with a carbon-carbon triple bond to give a ketone or aldehyde. To give ketone or aldehyde. Now, if we have a terminal alkyne like this case we get an aldehyde. Okay, the reagent for hydroboration oxidation Of course, we all know this. BH3, borane, followed by hydrogen peroxide in basic medium. What this does is to give you an aldehyde. This carbon here is this carbon, and this carbon here is this carbon. So similar to what in the case of mercuration, demercuration, one of the carbons become a carbonyl carbon and the other become a CH2. The difference here is the carbonyl carbon for the terminal alkyne will be an aldehyde. Now, how does this happen? This is also an addition of water. Okay, so let me ask you this. When we use this reagent here to add water to carbon-carbon triple bond or carbon-carbon double bond, is it a Markovnikov addition or anti-Markovnikov addition? Anti-Markovnikov addition, very good. And that is what is happening here. So if we have this, since we say the net process is addition of water, look at this. So the hydrogen is attached to that carbon. Okay. So we have the hydroxy here. Okay, good. No, I'm sorry about that. This is we don't have the double bond. We have double bond here. Okay, the hydrogen goes to this carbon here, and the hydroxy goes to this carbon here. And this is also an enol. And what do they tell you about enols? Very unstable. So they will tautomerize. The word that we use is tautomerization. Okay? Okay, so they will rearrange. Okay, what do we do here? We have form a carbon oxygen double bond, and this pi electron comes here, and this hydrogen here will now attach itself to this carbon. Just a minute. So this here, if we say this is compound A, this is compound B, A and B are tautomers. Yes. No, there is no hydride shift. No, it's just what we call this is tautomerization. When you have a molecule in which you have the rearrangement of the molecule so that the hydrogen moves from one part of the molecule to another, yeah. We call it tautomerization. I know what you're saying. That is in the case of carbocation. No, that's not what we have here. Okay. So now we could also make aldehyde as starting with a terminal alkyne. This is a terminal alkyne. By reacting that terminal alkyne with borane followed by hydrogen peroxide, then we obtain the final product. In this case, the final product will be an aldehyde, okay, not the enol. Even though the intermediate product is an enol, the enol will rearrange to form the aldehyde in this case. Okay, so that was 6. Jodwina? Okay. Of course, we know we could form ketones using Friedel-Crafts alkylation. We know that already. So this is 7, right? Friedel-Crafts alkylation. Okay, here, all we do, we take benzene or any benzene derivative. Say we take this here, and we use an acyl chloride. Any acyl chloride will do. In the presence of aluminum chloride, say acyl chloride. Okay? Yes, this is acid. Oh, thank you. Friedel-Crafts acylation. Sorry about that. Okay. Take any acid chloride or acid chloride in the presence of aluminum chloride. We then obtain, in this case, the methyl group is an auto para director. So we could get an auto product plus a para product. So let us simply show the para product. Now we could also, okay, that was 7, 8. Okay, linear reaction with a nitride. With a nitride. If you take a molecule that contains a carbon-carbon triple bond, it's what we call nitride, and you take any linear reagent, so let us use this linear reagent for example, say step 1 and step 2, hydronium ion, the nitride will be converted to a ketone. The nitride will be converted to a ketone. Okay, number 9. Hopefully by putting all of this together in one sequence, it will help you to remember all of these reactions. Number 9. Reaction of Gilman reagent. If you remember Gilman reagent, with acid chloride or acid chloride to give ketones. If I have this, molecule here, we call this acid chloride. And I have Gilman reagent. Let's use this here. It's a copper lithium reagent. We get this. Okay, so we could go from the acid chloride to a ketone using the Gilman reagent. Now, of course, the question is, how do we make the acid chloride itself? The acid chloride could come from a carboxylic acid, for example, this here reacting with thionyl chloride, SO. Okay, so this is the second time we are using thionyl chloride. When was the other time we used this? To introduce a chlorine, okay, to replace an hydroxide. Okay, very good. So in this case, this is also replacing the hydroxide of the carboxylic acid to give an acid chloride. And of course, we know this particular carboxylic acid here, we could obtain this from what reagent do we need here to go from this here to here? Trying to give you a review here. Potassium permanganate? Okay, very good. Indolute acid. So this would be a possible synthetic scheme. Starting from, the question could be starting from, right? Starting from this here, give a synthetic scheme for this here. I'm not saying this is going to be the exact question in your exam, but that's the kind of thing you should be thinking of. In other words, linking together all of these reactions. Okay. So I think we've had enough of the synthesis of aldehydes and ketones. Let us see what time do we have here. So we go to reactions of aldehydes and ketones. Yes. Yes. Sure. The Grignard, it gives a ketone. The Grignard reacts with a nitride to give a ketone. Okay. Okay, so I have given you 9 different methods for making aldehydes and ketones. So let us see now. So we still have plenty of time. Okay, so now let us go to the reactions of aldehydes and ketones. Reactions of aldehydes and ketones. I want to start off with what we refer to as nucleophilic addition reactions. Very important set of reactions. Nucleophilic addition reactions of aldehydes and ketones. If we have, well, let us start by saying addition of alcohols. 1. Let us start numbering again. Addition of alcohols to give acetals and ketals in the case of ketones. If you have this ketone here, and I have this, just take a regular methanol, okay? In the presence of HCl, the HCl will be acting as a catalyst, just a small amount of HCl. We will obtain this product here. We call this an ketal. If on the other hand, we use 2 moles, we make 2 moles of the alcohol available using the same ketone, HCl as a catalyst, we will obtain this. We refer to this as a ketal. The ketal is whenever you have the 2 moles of alcohol reacting with the ketone. In this case, the ketal is whenever you have 2 alkoxy groups attached to the same carbon, and that carbon is attached to 2 other carbon atoms. Then you say you have a ketal. Now this ketal here, under dilute acid condition, if I take the ketal, I add dilute acid here, what does it do? It will break down back to the ketone and the alcohol. Some of you will say, then what is the point of this reaction then? Okay? Under acidic condition, the ketal is very unstable. But under basic condition, it is very stable. So how do we use it? So what is the point to this? We could therefore use the ketal as a blocking group, as a protecting group. Okay, so let me go to, we're still on reaction 1, okay? Ketal as a protecting. I'm going to give you the mechanism of that reaction because it is very important. Supposing you have this. And I want you to go from this molecule here. There is some pharmaceutical drug that we need to make, in which we need to take an ester in the presence of a ketone. We want to take the ester to the primary alcohol. So this here, we are going to turn this to a primary alcohol, right? What reagent do we need to do that? Does anybody know what reagent do we need to use? lithium aluminum hydride. Okay. Well, that's what I thought you guys would say, which is very good. But if you did that, the lithium aluminum hydride will convert the ester to the primary alcohol, which is correct. It will also convert the ketone to a secondary alcohol. So in this case, before you could perform the lithium aluminum hydride reaction, what you will need to do, convert this ketone here, carbonate, to a ketal. Okay? Very often we use this molecule here, ethylene glycol. If you look at this ethylene glycol, it's almost as though you have two alcohols in the same molecule. By the way, this is the same liquid that you use as for your antifreeze liquid in your car, okay? Ethylene glycol. If you do that, then what do we have? We form the ketal. We see have the ester. Now we could perform our LEC reaction. Now you perform lithium aluminum hydride reaction, and then you follow it up with dilute acid. Okay? Now guess what happens? You reduce your ester to the primary alcohol, and then you're going to open up the ketone at the ketal back to the ketone because of the dilute acid at the end. Because once you do that, once you add the dilute acid, the ketal is unstable, it goes back to the ketone. Okay, so we therefore use the ketal as a protecting group in chemical synthesis. Okay. Okay, so that was our reaction one. We say we could form we could add alcohol to ketone and aldehyde. Now let us see what happens in terms of the reaction mechanism. Okay, you got this? Okay, I'll say mechanism of ketal formation. So we start with this here. Keep in mind, this is the reaction we want to follow here. Two moles here. HCl is here as catalyst. Okay. So the first thing that happens, the HCl acting as a catalyst will be providing a proton. So let us simply have the proton here. And keep in mind this oxygen here has a pair of non-bonding pair of electrons. Okay, so what happens? This non-bonding electron attacks the proton. Just a minute. Yes. From HCl. The HCl is acting as a catalyst, okay? This hydrogen. Now, once you protonate the oxygen, that makes this carbon here a lot more electrophilic. In other words, this electron now wants to go to oxygen, and what is going to now happen to make it easy for the alcohol this time to attack the carbonyl carbon and this pi electron goes to oxygen. Now we have this here. Now this oxygen is positively charged. Okay. Now we are now going to have a transfer of proton from this oxygen to this oxygen here, because ultimately we are going to be losing, we are going to lose this here, this oxygen here. Okay. So we have this. Just we'll grab this proton here, release this here to here. So now we have now this here, this molecule here, this intermediate is now set up to lose water. So this mechanism that I am giving you here, this is a typical reaction mechanism for the nucleophilic addition reaction, in which we are adding a nucleophile to the carbonyl carbon. Okay. Okay, so we lose this water here. And in so doing, what are we doing? We are forming a carbocation. And once we form that carbocation, what happens? Another molecule of the alcohol comes in, attacks that carbocation, and now we have, let us do this. Positively charged. Okay. And now, of course, keep in mind at the beginning we got the chloride from the proton from HCl. We are using this as a source of our proton, as a catalyst. So therefore, that will simply now come to grab this proton from here, and then that will release the electron to oxygen, and therefore you now form your ketal. Of course, this reaction, that mechanism that I've given you, is a reversible process. All of these reactions are reversible. So you could actually direct this reaction to go the direction that you want, You notice that here, we have is essentially losing water here. So the way you drive this reaction is to continuously remove water from the system. Okay? So anyway, so that is the mechanism for the ketal formation. And the same thing will apply if you add an aldehyde. Oh, time is gone. The same thing will apply if you add the aldehyde. So I will see you guys on Tuesday. And then when we come back on Tuesday, we are going to finish this. I was thinking of giving you a quiz on Tuesday, but we have not done enough. So we come back on Tuesday, we finish on chapter 19. Then on next Thursday, we begin to do some problems and quizzes on next Thursday. So enjoy your weekend. Yes. The exam is on March 6th. Oh, it's going to cover chapters 17, 19, and 18. 18, we don't have too much on 18 anyway. Yeah.